All right. So yeah, so it's been a while. I think it's been a week since we last had our study group, right? I know we had to kind of change things up. Thanks for working with me on that. But today we're going to kind of finish up optimizations, if I remember that right. That's what we left off on. We'll finish that up today. We'll try to touch a little bit on convolutional neural nets, which is like a form of deep learning. We can probably come back to it on another time too, and go into more detail if someone's interested, especially if it's going to be in your Mod 4 project. I was originally going to do transfer learning right after convolution. I think I'm going to hold that off for a little bit later, just because I want to be able to take that time to go over it, but still go into NLP. So the goal today, we'll see what happens, is to go through the rest of optimizations, introduce convolutional neural nets, convolutions. Oh, I see Christine's asking for the password. Let me just message that real quick. I don't know why it does that sometimes. But anyway,
the link that you sent already has the password.
Yeah, I know. So sometimes some people have issues with it. I'm not really sure why, but yeah, I should just go right in. But that's right. It's always the same password every time. Anyway, we are going to go through the rest of the optimizations. We'll kind of briefly talk about convolution. To be honest, if you're still kind of confused with convolution, I don't blame you. We can talk more about it. I'll show you a little bit of example of like when things go wrong with neural networks, which I think is kind of an important kind of thing to realize. And then we will go into natural language processing, intro and stuff. It's going to be more higher level stuff, like higher level, is that right? Like more general, like less of the code is specific. We'll still have some code as we get into it, but I want to kind of introduce what NLP is, strategies, and kind of a concept of it, and then we'll go into some coding. And so know again that like these topics, we can expand a lot more into it. So if you guys, especially in office hours, as we go into the project, if you guys are like, hey, I want to learn, like we really would like to learn more about convolution or more about NLP, could we go into more detail on that in a study group? We can totally do that. It's totally up to you guys. These things can apply to your Mod 4 project, but not everyone's Mod 4 project. So that's what we'll talk about afterwards. So we'll finish at the hour, so about 50 minutes from now. And then we'll kind of just go right into talk about the Mod 4 project. And the reason why I'm doing it a little bit earlier, it's technically a little bit earlier than we typically would. I like to give you guys kind of like an initial head start into thinking about the Mod 4 project. And honestly, most of the stuff, if you've gone through the material, you pretty much have everything you need right now to do the Mod 4 project. And that way, when we go right into finishing up the Mod 4 project and your assessment, you can go right into capstone. And in my opinion, capstone is the one that you should spend the most amount of time and really the most effort, because that's usually the one that's kind of encompass everything together. And it's going to be the project that you're probably going to talk about with your, like in an interview setting or with a technical recruiter. So that's why I kind of want to for kind of like going forward, I want your Mod 4 project to be like, I don't want anyone to have their Mod 4 project turned in late. I want everyone to have it in and done. And the reason why is not because, like, oh, I'm trying to be a stickler. It's like, I think it's important to move on to the capstone and spend that time there. Okay. Sound pretty good for today? It's the whole agenda. Awesome. All right. So let's just get started, and I'll share my screen. And of course I have a lot of windows open today, like more so than even before. All right, and unfortunately, oh, no, I don't see sorry, I'm pulling up the little Zoom. Oh, good. Zoom changed something for me. I think I like this better. Oh, well. All right, so we're gonna continue on with deep neural networks, right? Or sorry, yeah, deep learning. So we're gonna talk about convolutions, but deep learning, neural networks. We'll talk about convolution a little bit today. Transfer learning we'll save for another time. But last time we talked a lot already, pairs implementation, how we do a neural network, what is a neural network, how to avoid overfitting. We talked about activation functions. I think we talked about a whole bunch of this stuff, right? Yeah. And I think we got partway through optimizations, if I remember that right. Did we start optimizations? Does this look familiar? Vanishing gradient problem? Okay, I see some head nods. Cool. So I'll kind of go off from there. So let me just minimize this. It makes it easier to navigate. Okay. Like I mentioned before, is that basically your optimizations are kind of like to help you get to the answer faster. In a lot of ways, neural networks are kind of like when you teach a child, you don't have a full control of like a child, right? You can't control every single aspect of their life. You could try, but it's not going to work out, right? All you can really do is kind of like guide like the child in the right direction. that's kind of like what your neural network is that it's going to do its thing, but you can encourage it and then guide it in a direction that you want it to go. Is it going to do that? Not necessarily. So that's kind of what the idea of optimization is. Like, we can encourage it to basically converge, what we say converge faster to an answer, to a local minimum, or I should say, hopefully the global minimum, but a minimum of the loss function via gradient descent. Okay. So that's what we're going to do with optimizations. I kind of had some resources here shared on the notebook. Remember, you can find this all in the repo online, right? And for recordings, it's in the description. I think you guys know where to find it. I'm not going to bother with showing you guys again. But Keras, has a lot of things about optimizers that are actually built in. You can actually design your own optimizer too within Keras's API, which is pretty cool. And then there's actually a great post right here about optimizers and like what these different things look like. So if you're kind of looking for an extra resource on top of whatever the curriculum has and things that you've come across, I really like this blog. This blog that they talk about a lot of these optimizations, and it's nice. They kind of talk about I like when they show you equations, even if you're like a little more math adverse, which I think most people here kind of at least like are interested in looking at the math. It helps to look at the math and see what, like, try to look at this, like, what is going on exactly? Like, what are we talking about? And then what's really nice that this blog does a good job of like trying to explain it in addition to just showing you the equation, which I think is super helpful. Okay, so yeah, resources, and let's hear. I'm gonna kind of go through, you guys, I might repeat myself. I'm sorry if you guys already heard some of this, but vanishing gradient problem, we talked about this, of how the gradient basically can get too small and we can run into some issues with adjusting the weights and biases. Does that sound familiar, right? Okay, so one way we can fix this problem is just doing different activation functions. So just to recall real quick, the activation is basically, it's essentially just the function that allows like the inputs from like the neural network, to like one neuron, right? And so it gets all the inputs like a linear combination, and it says, all right, should this value go on to the next layer, to the next part? And I say this value could also be like adjusted, right? For example, in sigmoid, it would be between 0 and 1, right? With other functions like hyperbolic tangent, tanh, I'd be -1 and 1. But they do it in different ways. This, for example, ReLU, right, basically sets it to 0 if it's less than 0. So if it's negative, it just sets it to 0. Where we talk about leaky ReLU and all these good stuff, right? So a good way to basically avoid this vanishing gradient problem is making sure you have the right activation. So for example, I think I showed this picture before, right? I think this is pretty funny. I came across this randomly, and I just thought it was just a really good like kind of example of this. Like, yeah, like this is kind of more or less the order of like what you think of like activation function wise. Is that basically hyperbolic tangent? I'd say is probably like at the very least, like, don't use sigmoid. Probably hyperbolic tangent would be kind of like if you're not going to use whatever reason like ReLU or leaky ReLU or some variation of that. You can have this. I don't want to go too much into the details right now because there's a whole bunch we could talk about it. But basically, it saturates the activation. But it turns out this can actually be all right because there's some ways to get around it. So you will see people use hyperbolic tangent. You might still see people say sigmoid, but not so much anymore. It's just not considered very efficient. And then ReLU is kind of the more default now. As mentioned, I think someone brought it up. The curriculum does talk about neurons dying off, right, with the ReLU. So some solutions to that is leaky ReLU, which essentially, instead of having ReLU just have it set at 0, right, when it's negative, you have a little bit of a gradient essentially on that value. So that way you can learn a little bit, even if it's on the negative side. And then there's also, like, you can see a kind of reference here, this weird exotic neural network. Think exponential, like an exponential leaky ReLU. So like instead of having a straight line, for leaky ReLU, you have instead of an exponential decaying function. I guess not decaying. Well, it comes from the negative, right? It asymptotically comes up from the right to the left. I don't know if this is making sense. Does that make sense? I'm gonna just draw it real quick because I feel like I talked myself into a corner where I'm like, I can't explain it well. So you can think of like, this is the positive side. We saw like ReLU in red here, and it just go to 0. So we have leaky ReLU that would kind of like come off like this, like a straight line. And then you'll see things like, E-LU. I never actually hear people talk about it, something like that. But basically this is the exponential part. You can instead have an exponential function that goes like this. And it turns out this is actually pretty good. There's also other parts in there, but I would say do your research. If you start using these weirder stuff, like weirder than leaky ReLU, even leaky ReLU, you should understand like how you should, what's it called? How you should initiate the weights and biases. Okay. So anyway, for example, you guys know, oh man, I'm jumping all over the place because it's been a while. Don't initialize the weights all 0. That used to be something that people kind of like geared towards, and they said, okay, well, let's do a normal distribution around 0. And it turns out that's actually not very good. For the most part, for like hyperbolic tangent and even ReLU, you can just use randomly initiating the weights. That's not true for every activation function. For example, leaky ReLU has better optimizations if you initialize in other methods and stuff. And I'm not going to go into the details of that because again, we're like, you can see how big this how deep this rabbit hole goes. Like we can talk forever about just activation functions. Okay. But anyway, one solution is like, hey, let's choose the right activation function. Another way to basically try to avoid the vanishing gradient problem is actually having random starts. So the reason why vanishing gradient problem is an issue is that basically we get to a point where the gradient's so small that we're kind of like just kind of stuck. It's kind of like if you were imagining a like hill and you imagine like when we do gradient descent, like you're like a ball that's like rolling down the hill. If it's really steep, you're gonna find it pretty quickly, right? But the problem is that if it's like this really long like stretch that's almost flat but not quite, you would in some ways like, yeah, you kind of expect eventually to get there, but your ball is going to very slowly move forward. And you can also kind of think of like friction, right? Like, like you can kind of like, if you had a flat surface and you had a ball on top of it and you kind of lift it up a little bit, you could still have the ball there without it like rolling down the hill, right? That's kind of what's going on here. The problem is like, this is the real optimal spot, but it's just kind of sticking here. So what we can do, one solution is called random starts. And as you might guess, what you do is you essentially just start it off at a random spot. So essentially what this means is that to avoid like what we call local minimums where you get stuck, right, in one spot, we basically initialize the weights and biases in different places on the cost function. Like you can imagine like all the hilly valley and stuff like this. And so that way, if we run the model multiple times, we're starting it in a random spot, we're more likely to actually find the real, or at least a better local minimum than if we ran it once. Does that make sense to people? Like how that works? I see a couple head nods. Any questions on that? Okay, cool. All right.
So let me just say it in my own words and see if you agree. Mm-hmm. If I have a field and that field's got holes here and there, some deeper than others, and I just drop a ball each time from a different location above that field, it's more likely that at some point, one of those balls is going to find the area with the deepest hole.
That's right. Yeah. And so visually, like literally like kind of repeating what Alvaro just said, is like if you imagine like these holes, like these valleys, right? It's like there's a little local minimum. Here's like the real minimum. And let's say there's like another like minimum right here and stuff like this. Like what might happen is like if you drop like Alvaro's like analogy, like if you drop the ball that's like right here, the ball might end up just sticking around here because it falls in and then really can't get out of this point. But if you had started like right here, like it would definitely have fallen into this hole. And so the idea here is that you can have like try that basically each time you drop a ball essentially is running in the model another time with a different initialization. And this red, like, can anyone tell me like what does this red represent? Like when I point this like surface and stuff, like what does that mean?
The loss function.
Exactly, it's the loss function. Sometimes you call, you'll hear people say cost function and loss function sometimes interchangeably. Technically, it's the cost function. Loss is technically how it's changed, but don't worry about it. It's really the same thing. But yeah, it's basically how basically the parameters space. Like if you had the parameters in this space, would you get a smaller loss? And essentially, it's like, yeah, that's what this represents. So hopefully if you think of the rest of this stuff, and when you talk about neural networks and also just machine learning in general, is that your model is the actual ball. Gradient descent is the way the ball like tries to find the smallest point, and the actual surface is the cost function, right? So you can also think of the loss function, but same thing. Okay, cool. All right, hopefully that kind of gets you guys thinking about it in different ways and stuff like that. So, all right, so that's one solution. The other solution, which is one of my favorites, is momentum. So I love that we just call it momentum because it's like, obviously it's not, you know, like you think of momentum like a physical thing, it's definitely a little different. And this is where I think the ball analogy works really, really well. But basically, just remember that gradient descent is finding the lowest point in the cost function, right? And we represent that with J by basically just adjusting all the W. Like you see this capital W here, this is representing saying all the weights, right? The vector of weights and stuff like this. So not just one weight, but all the weights. And basically the cost function is determined by, if you had this weight for this value and this weight for this value, you would get a, I have the cost function, you have a cost of this much, J, okay? And we can basically say, well, okay, we can fall down this mountain, right? Well, the thing is that we're gonna take steps, right? Based on how steep it is and the actual learning step, right? Size, which is alpha. Okay, does that make sense so far? So this little equation right here, which you'll see sometimes, the way you read this is that this W and this arrow right here just means like updated, so you can think of it like equals, like we've been doing in programming. But basically that we're going to set this W, which is a vector of all weights, by basically setting it to the original weights minus some some step size alpha times the gradient of the cost function for that weight value. Does that make sense? So essentially what we're doing is like this JW is us right here. This is the gradient right here. Basically it's the derivative, right? Is that it's saying, okay, how steep is it right here? And then say, okay, if it's really, really steep, you'll have a bigger step, right? And then we just scale that by some alpha. And note that we have negative. The reason why it's negative is basically because we're going against the gradient. So that's kind of why what's happening, this negative part. But that adjusts our weights to a new weight and we get a new spot. That's what we've been doing before. Nothing new here, just kind of new way to like read it. Okay? But sometimes, like I mentioned, we get trapped in like a local minimum. So for example, I have this little picture here I drew. I'm a great artist, aren't I? You can see that what we would probably do is like, if we didn't have enough, you know, oomph, right? Whatever that is, right? We would get like, you know, we say, okay, we take a step over here. It's like, oops, let me draw. We would take like maybe a big step right here. That would be us right here. And then say, okay, now we take even a bigger step right here. And we take another big step right here. And they're like, okay, we're here. It's like, oh, we take a small step. You know, maybe this is a little small spot right here. Maybe this is the actual minimum we hit. Like we start going this direction, like, oh, like, nope, that's too far. We just go back. And we might just go back and forth along this line and never really go past this point because the gradient's so small, there's no reason to keep going. Where really, if we get past this little hump, we'd go here, right? And this is where, like, you know, maybe you could adjust alpha, right? But then the problem is with alpha as well is if you made alpha too big, which would get you over this hump, you might also overstep these minimums. You might completely miss it. So that's one reason why we can't just simply just adjust alpha because we don't know. So the idea here is kind of analogous to having a ball roll down the hill. It's like, well, what if you just give it some little extra oomph, some little extra momentum to keep going in the direction it's going? And that's what this momentum optimization is called, or doing. And so there's a couple ways we can actually implement this. And so this one right here, we can like, I kind of wrote here, like power over the hill with momentum. So we can basically update this W, our weights, with W plus some kind of extra bit of like velocity you can kind of imagine. And this velocity is the same thing as before. We're still doing the minus alpha, the gradient of the cost function, okay? But we're adding this extra bit right here, which is beta times this, I think I called it a velocity here. No, this velocity item essentially. And essentially it's like this velocity item right here gives us a little extra bit, right, to keep moving forward. Note that it's in the opposite direction, or it could be in the opposite direction of the gradient itself. We could keep moving even though the gradient's pointing the other direction. And that's the idea of the momentum. Now, the big question is how do we actually find this VM, right? How do we determine what VM is? And there's a couple ways we can do that. One is saying, okay, like we can essentially look at like where we are currently and saying, well, what direction were we going prior to this, and just use that. There's another way, which is the Nesterov momentum. And this is kind of cool because it looks at basically the gradient where it would have been, or where it will be, and saying what would be my my direction if I was over there, and then using that direction. It turns out Nesterov actually works really well compared to, in general, compared to looking at your like you can think like your current position versus like what you would get if you kept going. I don't know if that makes sense to people, but it actually turns out to optimize a lot. It's kind of like, if you're familiar with physics, it's like a dampening factor. That's kind of what's going on here. So that's why we're able to actually implement this. And actually implementing it, at least with Keras, is actually really, really simple. Like you can see here, there's Nesterov equals true in momentum. That momentum 0.9. Guess what that is? That's just beta. And you're like, oh man, another, like, most people's like, oh shoot, another number I have to like worry about. Like, what am I supposed to set this on? In general, like 0.9 usually does pretty well. And again, it's kind of like a dampening factor. So that kind of makes sense why, 0.9 is pretty good. You might see up to 0.99, but 0.9 is probably going to do perfectly fine. If you're not getting it on there, there's probably other things you can do. But it makes it nice and easy for you to optimize this. Okay, cool. Any questions on that? I think it's a pretty, like, you're like, oh yeah, duh. Like that seems like a good thing to do. Just keep going in the direction so we can overpower walls. Implementing is kind of I think it's pretty cool. Like I think the Nesterov method actually, it's a pretty cool like look to how you would optimize this. Okay, no questions then? I can move on. Sounding pretty good. All right, I think I see mostly like confirming faces. Nothing, no one looks too confused, so I'll take that as a good sign.
Yeah, and that blog that you showed before, I've actually read that before.
Okay,
and
perfect.
It's really, really good. It's really, really
It really
clear.
is. Yeah, right here, like talks about Nesterov. Like I love this blog. Like definitely, if you guys haven't, if you hadn't come across it already, like, and you've seen that in my notebook, go check it out. It's a great read. So, and I think like you guys should honestly look at what other people say and how they talk about it, because it's useful to see different perspectives and different ways people explain things. Okay, cool. Thank you, Vera, for chiming in on that. All right, so some other things you can do for optimizers. We'll try to go through this relatively quickly. Say less than 10 minutes. We'll see. I like to talk a lot, I guess. One is normalization, batch normalization. This is something that's been so this is a little interesting because recent research might suggest that batch normalization might not actually be necessary, but it's also like not a bad thing to do. And basically what it is that normalization, you guys know what normalization is. It normalizes on the batch normalization. And this allows, like, say speed your training, and that's what they've seen. So one thing that's interesting is that it does speed up, it seems to speed up the training itself. So your epochs, are more efficient. If that way that you get to the answer quicker. However, it does like slow down the actual training. Like each epoch tends to take longer. But in general, like they kind of balance each other out, and you usually end up coming up ahead of this. So in general, like batch normalization is just a good thing just to have in your, actually in your like neural network itself. But of course, like there is some recent research that's kind of like questioning about saying whether we should or not. My suggestion is it's not like, I always use batch normalization when possible. There's not really too much of a trade-off to it. And it usually does pretty well. Okay. So anyway, that's pretty quick. I'm not gonna go into the full details of how that works because I think we don't need to talk about it in a lot of detail.
Question. So in batch normalization, what we're normalizing are the actual weights, right? Basically the input to the neuron.
Yeah, it's kind of treated, you can almost think of it like a layer, like almost like the activation. Like if you're building up like with Keras, and you, instead of like passing in your layer and having the activation, you can just have the activation with Keras, like after your layer defined. It's kind of like with batch normalization, it's the same idea. And so it's just doing it per batch to help normalize. So essentially, so you don't have very large values. And that's the reason why it tends to speed up faster. I mean, I'm sure there's a whole bunch of more research that, people can talk about and stuff like this. I'm actually trying to pull this up, but you can think of it as like a layer itself on top of like, once like this first layer is done, you now have batch normalization, and that can go forward. Technically speaking, like you should normalize your data before you pass it in the input layer, because otherwise you have very, very large values. The neural network's going to have a hard time adjusting those large values. But if you have a batch normalization layer, you could technically just like skip over that part. That's kind of like the idea there. So I don't know if that kind of clears things up, but yeah. Cool. All right, continue on. All right, so stochastic gradient descent, we know this, right? Stochastic gradient descent. Notice stochastic right here, you can think of it as random, right? And basically, instead of like always going the optimal direction every single time, the thing is, it's like you can imagine like to do the optimal direction, like you have to like do all the fine-tune calculations and stuff like that, and then like think about it for a long while and say, okay, now I'm going to take a step. Stochastic gradient descent kind of takes advantage. Like, well, you don't need to go the best direction, just like a good enough direction, and we'll kind of balance it out because we're doing it randomly. And so what you'll see, excuse me, is that basically you'll tend to hop around a little bit more. So it seems to be a little more like jagged in the direction it goes. So sometimes the loss will be higher, sometimes it'll be lower for each epoch going through, or even just each batch. But what happens is that in general, you end up going down the hill quicker, and it just gets you out faster and faster and faster and faster. Okay. So the steps you can kind of think about this, like when you do stochastic gradient descent, you take a random batch. So you take a set, like some subset of the full data, that's your batch. You feed it forward through your model. You calculate the loss from that batch, and then adjust the weights via propagation, and then just repeat the whole thing. So if you think about this, this is your epoch right here. Like you're doing one epoch, but you're only doing it on a subset of the data. So you remember the cost function itself is defined by all of the data, right? And how the weights basically have the minimum based on that whole set data set. So instead of us considering all the data, we're just going to consider a batch at a time, which I don't know if about you, that might sound like, it's like, oh, that seems like not a good strategy because you're not considering all the possible values, but we're just trying to get there faster. So what we can do essentially is like, well, we're only consider a subset at a time. And hopefully is that our data set in a lot of ways has a lot of repetition in it, right? There's a lot of repeated patterns in the data. Like not each one data point is special by itself. It's like collectively it's a pattern, if that makes sense. So we can consider subsets and we're still gonna go in the general direction towards it. And it also means a lot faster. So instead of having each epoch take a very, very, very long time, instead what can happen is you can go there a lot faster by basically taking bigger, well not bigger, but like the general, you can calculate the steps faster. Hopefully that makes sense. Because so real quick, pop quiz. Of all these steps, like obviously number 5, just repeating it, of all these steps right here, what takes the longest time? Like what's the thing that makes neural networks take a long time actually getting to an answer for an epoch?
Is it backpropagation?
Yep, Akiva, and I saw that Brian put up number 4. Yep, that's right. It's backpropagation. This is the thing that's going to take the longest time. So the thing is, if we have a lot of data and we try to do backpropagation, we have to consider all these data points and how it affects our gradient. So if we can optimize that part and still get good enough answers, like this can speed up our training significantly. And that's the idea of stochastic gradient descent. Okay. Any questions or comments on this? Moving on then. All right, we're gonna try to get through this stuff pretty quickly. So next thing are some, you'll see this often like Adagrad, RMS, Atom. We're gonna talk about a few of these things that are optimizers. I'm not gonna go into full detail about exactly how they work, but it's kind of useful to like know a little bit where they are. Just a quick like note though, basically don't use Adagrad. It's not, it tends to stop early for a lot of complex problems. You could use it for some like simpler problems and stuff, but if it's too complex, it will stop too early and won't reach what's it called? It won't converge to the optimal solution. It'll stop too early. So RMS prop is kind of similar to Adagrad, like how it works too. It tends to be a little bit better, but in general, just kind of be aware of these things. What was I going to say about this? Yes, so one thing is basically, it's all about saying how big of a step we take. So instead of taking the same size step every single time, what we can do essentially is use an autograd and an RMS prop. Basically what we do is consider, as we're going through, is for autograd, we take the average gradients as we're going through. So as we're going through each, saying, okay, this is the gradient, this is the next gradient. Instead of going off of just that one gradient, we take the average of all of those past gradients. Does that make sense? So like if you are, where's my drawing tool? If you imagine you're up here and you guys know how to read these, like, hopefully this makes sense. This is like a topographical kind of map, right? And you can imagine that like this right here is the lowest point. So if I were to imagine like I'm like right here, right? I would take like, oh, this is a really steep spot, so I'm gonna take a bigger step. And then as we get into like, let's say, I'm using stochastic, so I'm not going the most optimal. Say, okay, then I'm going to go this direction right here, right? My steps are going to get smaller as the gradients over here. So the problem is like, now my gradients suit like, it's much smaller and it's gonna take me a long time. So maybe this happened like 2 steps and then the rest of it is gonna take like me 50 steps, for whatever reason. So 50 steps, like 50 epochs. So the idea with AutoGrad is that we take the average of these gradients. So we kind of like combine these together so we can kind of like boost. It's like, well, we were already moving in that direction, kind of like momentum. It's a little bit different, obviously, but we're considering our past stuff and moving that direction. The issue with AutoGrad is that basically it dies off too quickly. And that kind of happens with, if you think about averages are affected by outliers very easily. So since you're taking iterations of like all these past ones, your outliers basically overpower. Well, the outlier in here that would be a big issue for slowing down is any small gradients. So these small gradients start adding up to it too much and essentially slows you down too quickly. So one solution to this is RMS prop. And RMS prop basically allows us to do the same thing where essentially we're taking an average of the gradients, but we do a weighted average. So basically more, oh my gosh, it's a decaying average. So essentially we consider more, we basically kind of adjust the weights. That way we're not averaging completely off and it's less affected by outliers and stuff. So this tends to converge a little bit faster and tends to be a little bit better than AutoGrad itself. Okay, but they're the same concepts. All right, any questions? Does that make sense to people? Thumbs up if it made sense. Thumbs down, you're like, I don't know what happened. Okay, see, mostly thumbs up. All right, cool. So I'll move on then. All right. Oh, I just put a little code, you see. Easy stuff. Oh yeah, this is the learning rate right here. So you can still adjust your learning rate. Row, oh man, another number. Guess what? Probably just keep it 0.9. Usually like you don't have to adjust this too much. Thankfully, right? This actually works out pretty well. But you see, Keras is just amazing. You don't have to think about it too hard. You can actually implement it directly in here. Last one comes through, which is probably the one that you're most commonly going to use, is ADAM. Just adaptive moment estimation, right? Some acronym. There's also variants of ADAM, which I'll talk about, which is my favorite, is like NADAM, which is basically Nesterov. But basically, it's that it combines like the momentum and RMS prop strategy together. And so basically, there's like, I'm not going to go through the full details of exactly how this works, but basically, it's that you are combining these two concepts together and are able to basically approach the solution pretty well. So ADAM's like pretty good for like most sets. Sometimes you might come across where like it just, for certain problems, it just doesn't do very well. And it turns out like for those problems, if you just use Nesterov, like an ADAM, so ADAM with Nesterov momentum, it tends to work perfectly fine. So basically what my suggestion is probably use ADAM at first, but if you know a data set that you have, like someone else had done this and they had issues with ADAM, or you find that it's just not converging to where you'd expect it to, it might be worth trying to do NADAM. And in general, I honestly use NADAM more now after learning a little bit about this issue. And it doesn't really change too much if you use Nesterov, at least in my experience. Okay. So, yep, those are all the little adaptive optimizers. Probably this is the one that's most common that you'll see. Like if you look on Kaggle, I guarantee like if anyone's using a neural network, you probably see ADAM like everywhere. Okay. Cool. All right, I'm a little past my 10 minutes I said, but I'm going to finish it up with the last bit, which is pretty simple. It's learning rate decay. So this is kind of like, we talked about strategies to say like, okay, how do we use the gradient to adjust? But you can kind of imagine like learning the real, like in a lot of ways, like, oh, if we could just like adjust like the learning rate, like as we get closer and closer to the solution, we don't have to take as big of steps. So like the problem is like if we have a high learning rate, we might move too fast and jump over a local minimum. But if we have it too small, right, we might take too long to finally get to the small answer or the local minimum and make it forever. So like there's advantages and disadvantages. So what's our solution? We do both, right? So basically we start off fast. We basically have large, when we have a large gradient, we have a large alpha because we can jump down the mountain really quickly. And then as we go further along in epochs, we just make the alpha go smaller and smaller and smaller. So we can use something like an exponential decay and stuff like this. And what's nice again is that good old Keras has a good old optimizer that we can do. So you can actually set the decay in here. In this case, you can play around with this a little bit, but basically just saying how much is the decay every step going forward. Okay. And note that like on here, you can have multiple like things you can do. You don't have to do just one of these things. But a good place to start, I think in general, is just using ADAM or NADAM and Keras in general usually does a pretty good job. Okay, cool. Any questions at all about this optimizers? Feeling pretty good? Yeah, go ahead, Jessica. I think it's
hello. Yeah, I have a question. So if n atom is better and similar, why don't more people just go with n atom?
I don't know, to be quite honest. I don't know if like people just don't think about it. It's something that I find more efficient, and I think my guess is that it's the classic, like, you learned about this, you're like, oh, that's really cool. And then research came out saying, oh, like, it does really well, but there's sometimes it doesn't quite do well. And if you just add Nesterov, it would be better. But I think just a lot of people have learned Atom in general, and maybe that's why. That's the closest thing I can think of.
Isn't it part of it just that when Atom was developed, it was developed with a regular momentum, and so it's just the vanilla flavor of it, and later on the Nesterov was added as an option, and so I mean most people were used to using Atom with we're using regular momentum.
Yeah, I think that is, and I think part of it is just the fact that Atom already does pretty well to begin with. So even adjusting it, like, I don't think when it first was being used, people realized that there was like, you could make it slightly better by using Nesterov. It seemed like pretty comparable.
Because I kind of remember with Fast AI that they were kind of scrambling at one point to add Nesterov to Atom in their implementation.
Yeah, and that's why you can also see here, it's as Nesterov is not an option in Atom implementation, you actually have to pass an Atom for Keras's API. So like you can kind of see is that like at least the evolution of this, it wasn't directly added in there. Maybe if you were to start from scratch, that would be, but that's kind of the state we're in. So yeah, and I'm sure over the years you'll probably see other optimizers that more research being done, just like batch normalization now is kind of like not controversial, but kind of going like, oh, do we even need this? There's some discussion about that too in the space. Yeah.
Cool, thanks.
Cool. All right, so sound pretty good. Any other questions about optimization stuff that we went over today or maybe last time? No? Awesome, cool. So let me go ahead and I'm going to actually stop sharing. It's going to be a little bit easier for me. I'm going to go ahead and pull up our convolution deep learning. Oops. Where did it go? Sorry. Remember I said about too many windows? It's happening again. All right. I'm just going to share the screen again then. Cool. And I see that we still have about like a little over 15 minutes from our hour mark. We'll see how we go through. I'm not going to spend too much time on this because I think we can talk about it again in the future for CNNs and stuff like this. But just kind of know convolutional neural nets in general are just kind of like another way of doing deep learning. And essentially what we're doing is when we're doing deep learning, when we're doing neural networks, you're hoping the neural network is going to basically, the architecture itself can basically find general solutions, if that makes sense. Like a neural network can be made to do any function. However, it might take a long time for it to find the optimal solution. And there's no guarantee that you'll actually get the right solution that is like technically the best way to approach it. And convolutions are basically a method to say, hey, let's structure the neural network in such a way to encourage the neural network to actually find, a decent solution. And so we'll talk about that, and especially with images, but note that CNNs also can be beyond just images itself, which is kind of important to just kind of know. Okay, so let's see here. Neural networks are bad for images. So this is kind of like my clickbaity title, right? Ooh, it's super bad. So one thing to kind of note is that if you have an image, like with a neural network, we can only pass vectors in. And so when you think of like what an image is like a 2D array, well, at least a 2D array of pixels, right? So like I think everyone understands what like pixels are and stuff like that, hopefully at this level. But basically you say, okay, there's a whole bunch of values, right? Basically the values usually go from 0 to 255 for most cases, for each basically saying how bright he thinks they are. That's for grayscale, right? So it's 2D. Technically when we have like colored images, we have like each channel, and for like a color or for gamma or like stuff like that. So for example, you'd have red, green, blue, and combinations of red, green, and blue pixels with different brightnesses caused us to perceive different colors, right? So that's kind of essentially how basic images work. So essentially what it comes down to is basically images are essentially a bunch of just numbers, right? It's in some kind of matrix form, or I should say tensor in general, okay? So the thing about that is like, well, how do we like pass this into a neural network? Well, really we need to feed a vector. We can't really feed in a matrix. It's just, that's not just how neural networks work. So what we have to do essentially is make the, take our 2D image and we call like flattening it to a vector. And one of the easiest ways to do this essentially is to like, if you imagine, I'm gonna draw real quick. Come on, Zoom, where's my tool? Maybe I won't draw right now. Sorry, I'm trying to find my annotation tool and it's just, oh, it's behind the other Zoom window. Okay, that's new. All right, so if I draw right here a little quick picture of, I'm just gonna do like 3 by 3 pixels. Okay, and so if you imagine this like pixel A, pixel B, pixel C, pixel D, pixel E, pixel F. That's all I'm gonna do because I don't need to put everyone. And I convert this over now into a single vector, a one-dimensional vector, right? Well, I could just basically take each row of pixels and just kind of Frankenstein monster them together, right? And say, okay, then my thing's gonna look at pixel A, pixel B, pixel C, pixel D, pixel E, pixel F, okay? And you can imagine like that's now my vector. Okay, well, I guess I could go G, H, I, right? Keep going, but basically that's kind of how I do it. There's an issue with this, right? Is that we're losing spatial information. And what I mean by that is kind of a subtle point, but it makes a lot, like, it's kind of important. When we look at pictures, when you're like, say, for example, like, oh, someone's, like, there's a picture and there's an eye in it, is that these pixels right here are more closely related than they are to other pixels in the picture. Does that make sense, right? Like, it makes sense. Like, the pixel for an eye, right, it's going to relate more than the pixel over here that might be for someone's mouth or nose or something like that. The problem is that now what happens is that this pixel, and this pixel kind of lose a little bit of information. We don't, like, they're all considered equal. In fact, maybe even like these are closer together. But like, there's not like a way to, like the way we have it structured, it's not keeping that information, that spatial information that, hey, these are important together. And that's where convolutions are going to do a really good job. But like a vanilla neural network, it's just not going to be able to figure this out because it could potentially do it, right? Could figure out, hey, it turns out like, you know, every third pixel actually is another, you know, like it's closer together. So we should consider those parts, but it's going to be hard for the neural network to do it. Just like a child, if you were to just like have a child and have it never learn, you know, math and just say, all right, here, learn calculus. Like, could they learn calculus on their own? Maybe, potentially, depending on the child, depending on the environment, just by lucks, maybe even. But it's probably more fruitful to kind of guide them in direction to the point where then now it's like, okay, now you can do calculus. Like, oh, now you have all this experience and some stuff. And that's kind of what convolutions are doing. We're kind of guiding the neural network to say, hey, like, try in this way. Try to think of it in this pattern. And that's kind of what we're encouraging. But just to emphasize is that this, I think the curriculum actually shows an example of like using a neural network for images. It's not really like the best thing. And the only time this really works is with like the really simple data sets. So for example, MNIST, which I think you guys have seen at this point, is these numbers and stuff like this. You could technically try doing it on this one and it does a decent job, but it turns out it's just not very good. So I'm gonna skip over this, like actually coding this up. Basically, it's just basically doing a neural network and then we evaluate it and actually get something, I think, if I remember right, it got something around like 96% on the test data, which is not bad, but like, this is like a really simple picture. Like I can't remember how many pixels by pixels this is, but you can see the pixels on here. Like it is like really easy to see, right? So it turns out like when we get more complex pictures and stuff like this, you need something more complex, which is what convolutions do. Okay, makes sense to everyone? Kind of like that motivation, like why we're doing this? Okay, cool. So let's talk about convolutions real quick. So a convolutional neural network is a neural network that's going to incorporate a convolution. We also call them CNNs, right? So convolution neural networks. Okay, you see a lot of abbreviations in deep learning. Usually it's associated with computer vision and images, but it doesn't necessarily have to be. It's also can be really useful in speech pattern and like other like audio images. And it kind of makes sense when you think about it, because convolutions are really good at saying, hey, these things that are close together are related in some form or fashion. In the same way like we hear like speech or audio, the last like, I don't know, I'm no music expert or anything like that, but like the last like audio signal at the, like it's more close related to the signal right before it versus like at the very beginning, right? Like they're not separate from each other. Like it does matter between those two parts. I even seen CNNs used for natural language processing for like words and stuff like this. And it kind of makes sense that words closer together tend to have a closer relationship than words that are further apart in a sentence or in a paragraph. So that's kind of where CNNs can be really good. You can think of it as like patterns that are closely bundled. And again, closely bundled, it sounds like spatial, but doesn't necessarily have to be literal spatial closeness. Okay, so this is an example right here. I literally just like searched Google convolution neural nets, right, and pulled this up. Basically, one nice thing about CNNs is that we can just use it, the same optimizers. It's still a neural network. We can still use neural optimizers. We can use the same loss functions. Like we don't have to worry about saying, oh, we have some weird, new architecture. It's like, oh, we're just basically doing a neural network with some extra pattern finding layers. And then we can just have a layered network, just different architectures and stuff like this. So it turns out we can actually kind of build a convolution neural network pretty much like we would do for a neural network itself, just adding these extra layers. So we'll talk about briefly convolution layers, which essentially are just trying to find these patterns. And then we'll talk about max pooling, which really is just kind of like averaging things around. And then typically like a CNN, you typically kind of see like convolution, some kind of pooling layer, and then a convolution, pooling layer, and pooling layer. And we'll kind of talk about this a little bit more. But one thing I kind of want to point out is that the goal of a convolution is basically to take spatial information and reduce that instead into conceptual information, if that makes sense. It's kind of like equivalent to being like, for example, if you say, hey, is this a picture of a dog? And you say, well, and you haven't looked at the picture. You just ask them like, hey, this is a picture of a dog. Like, is this a picture of a dog? And you say, are there eyes in it? Like, oh yeah, there are eyes in it. It's like, okay, like it could be a dog. Like, are there whiskers in it? I don't see any whiskers. Like, okay, maybe it's not a dog. Like that's kind of like the idea of like the time it gets to this end right here is you're saying what conceptually is in the picture versus like, oh, look at the 54th pixel from the right. Is it white or black? And like that's not going to give you as much information. It gives a lot of information, for each pixel, but it's more spatial versus like conceptual. Does that make sense? Okay, and that's really what's going on here. And so you'll see is that you have like this these channels right here. It starts growing like wide in depth. So you can see there's basically more of these kind of layers where you start off with like a black and white image where it's just one layer, or it's not one layer, one matrix, one tensor, and it expands outward longer and longer. And you kind of see this general like expansion of from convolutions. But you see that very small here, but the resolution of these values is smaller and smaller to the point where it might not even represent anything that's technically visual. It might actually be much more of saying, oh, it has a whisker or eye in there. Obviously, just like latent features, I say latent features of the hidden layers for a neural network. It sounds like a good movie. Latent features of the hidden layer. I don't know, but that like hidden layer isn't literally like a real feature that we as humans would probably come up with. It's something that the neural network just found like, hey, this is what optimizes it towards this loss function. Same thing happens here. We don't know exactly what this is. And there's ways we can observe it, but it's, again, much more like a black box. And then at the very end of this, we connect it to a traditional fully connected neural network, multi-layer perceptron, right? And basically say, at this point, it says, hey, we have a bunch of features, essentially. Take these features, right, this vector of features, and basically figure out the patterns within there and give me a classification. Okay, does that make sense? Jessica, go ahead.
Yeah, thanks. So is flattening just reducing the pixels?
Mm-hmm.
What is flat? Yeah.
Well, I shouldn't say it's reducing the pixels. It's more like it's taking it, like when you say flatten it, it's like, oh, you're putting it into one dimension. Like that's really what's going on. Does that make sense? That
as opposed to...
Mm-hmm.
Go ahead, I'm listening. No, it's okay.
Oh. So as opposed to like for example, like max pooling, which we'll learn maybe in a future time, really is just saying like... I
understand max pooling.
Yeah, it's like that's reducing in a lot of ways the resolution, reducing the number of pixels, reducing the amount of information spatially. Where flattening doesn't necessarily reduce the information, it just organizes it into something that can be processed through the traditional neural network. So this flattening basically is taking, like, you can see there's still dimensionality to this, like if you kind of see this example, it's like a 4 by 4 by n by 2, and we want to reduce it so it's now just a vector essentially. Like you can think of it like your vector is now each input. It's just saying it's this feature or this value. So just think back to like taking our 2D image and then converting it into a single vector. That would be flattening. So that's kind of what's going on there.
Gotcha. Thanks.
Yeah. Yeah, no, good question. Because yeah, it's not, we're not losing information necessarily. There might be a step in the middle of the flattening, like you might have a different like step right here, but it's just reorganizing the information so we can process that. All right, cool. If we have a few minutes left, I guess I'm trying to think what we have left here. Tell you what, I will just kind of quickly, we're not going to go over this, but I'm just going to quickly show you. We'll talk about this another time, but I just want to say real quick, like we have different parts, for example, like the convolution of layers itself. We talked about the pooling layers, so I mentioned about max pooling, average pooling, and then the fully connected layers. I just want to point out the convolution, like how does convolution work? Basically, you just look at like, we call it like a window, and we just take that window and look at just those small set of pixels, and we combine those small sets of pixels into essentially like one value, essentially, right? So we're reducing, saying, hey, okay, look at this 3 by 3 pixels, these 9 pixels, and reduce it to a single value. So you can see we're losing in some ways information, but we're also finding patterns in there. You might say like, well, how do we do that exactly? I'll show you guys a quick example before we, I think I'll probably end on kind of convolutions for today at least. But you can kind of see it's like as this drags across, it's kind of hard to see because it's moving a little fast in this animation, is that this 3 by 3 like window is reducing to one value right here. And you can see at the very end, this whole image right here, or this, I should really say this matrix of it, data, like these data points are being reduced to a smaller version of this. But the idea is hopefully that this contains more conceptual information versus spatial information. Does that make sense? Like kind of like the idea of like we're reducing information, but we're now finding, like hopefully this is giving some information about saying this is some kind of pattern. This is where if we had more time, I'd probably go a little bit slower. We'll probably do this in the future. This, for example, I love this. If anyone, has anyone seen this blog post before? Like this is a really fun one if you guys are curious. I'm just gonna send it on the chat real quick. Where's my chat? Oh. Zoom is trying to mess with me today. There we go. Okay, so you can just see like this is like a grayscale image. This is the resolution natively, and you can see if I just drag my finger, or not finger, my mouse on here, you can see these are just little values here for each pixel and stuff like that. That's really what the computer sees is this guy. And so you can actually have like these filters right here, which is what basically the idea of these convolutions. And you can see here is that like this little red on the left right here, it's like those 9 pixels together are going to combine in some form or fashion, basically usually a linear combination into this little square on the right. So you can see here, like this image, this input image definitely has more information than this right image, but now we're like highlighting essentially, like it looks like we're highlighting like outlines and stuff like this. This is what the sharpen kernel. And it's all it's defined is like, oh, just take the pixel on the top left corner, multiply it by 0, add whatever the next pixel over here, -1, and so on. You can see this pattern right here, right? Then if you change this, let's say for example, outline, you can see these values change right here, and it changes actually what kind of pattern we're doing. And so again, we're losing information from each like convolution, but what's nice is that we have multiple filters. So we're not just looking at just the outline. We have essentially an outline, a subble, you know, identity. Like, this is like just defining what it is. The identity is just the real one, or like just one. But you can see like how you can change these values to get different like results over here. And reality is like, it's like, okay, like, do we put these values in? We don't put them in. Guess who puts it in? The neural network does. The neural network figures out saying what's the most optimal way, and right, it's going to try to figure out what values it. So again, that's why these filters on the right might not actually be real like features in some ways that we have. It actually turns out to do a pretty good job of finding features at a higher level of like saying, oh, like this is like, you know, you'll start seeing patterns of like different like if you do for animals, you might see patches of fur essentially in these patterns and stuff like that, which is pretty cool. But anyway, that's kind of the idea of these convolution like layers and stuff. And you can see here, it just all depends on what value here. You can actually, if you play around with this, you can actually do like live video, choose your file and stuff like this, and you can actually play around with the values. You can even like adjust these and stuff like that. So I think it does a really great job of like trying to like like the great interactive example of like saying what's going on with this actual filter part. Okay, cool. And just know there's other parts we'll talk about maybe next time, but there's a bunch of different parameters you can do to adjusting how it's going to actually go across the image and kind of reduce the spatial information. Okay. Avero?
Yeah, just kind of an interesting thing is that I heard that though it is convolutional neural networks, really should be cross-correlational neural networks. Because when you look at the whole thing from signaling theory, this is not, they're not really doing convolutions, they're doing cross-correlation when they do this. And I didn't come up with this myself. I heard that from Andrew. I heard Andrew Ang mention that.
Yeah, and that's interesting. I haven't heard that specifically, so that's interesting, like an interesting take from it for sure. I don't really know the full history of convolutions. Like I claim not to be an expert, right? I don't try to say I know more than I do. But like I wonder then, like, you know, sometimes people like use it in certain contexts and just becomes the way they use it. But yeah, you can kind of think of like really what it's trying to do is trying to find like patterns, which I think correlation might be a better kind of way to address that. Again, I'm not an expert. I actually don't know what the original, like when someone says convolution, if that's supposed to mean something different. So yeah, good to know.
Yeah, there's actually, if you look, you know, you do the Google search, there are a lot of articles on convolution versus cross correlation. And so it's just an interesting thing. You never know when somebody might ask you, try to trick you.
Yeah.
So what are we doing here? Yeah, I say, well, it's a CNN, but it should be a CRNN.
Yeah, that might be like the, like, actually, like, it should be this thing. And that's where, like, again, like, that's kind of new to me. Like, why you should always, like, look at other sources and see what other people are talking about and stuff. For the record, if someone does try to trick you on that, that's kind of a mean thing to do, I think, in general. But, like, I think if you kind of, like, get the idea, someone says, well, tell me how convolutional, you know, CNN works. And like you're able to kind of talk it through and say, okay, this is how it works. Even if you aren't like literally writing the code, like not even the code, but like writing like the mathematics, like that's going to be like sufficiently, like much more sufficient in my opinion. Like I don't think I ever would really care if someone could tell me the actual mathematics on it, because why does it matter? Like it's more important to understand like what's going on here at the higher level. But anyway, it's also useful to know the underlying mathematics just because you can build up on it. Okay, cool. So I know we could like talk more about this, and we'll try to talk more about it in the future. I did want to point out just one last thing, just kind of like this whole like idea of the features, or not features, these layers. So you can see here, like this is the first convolutional layer, and these are the different filters. Like these are some of the filters. This is taken from one of the blog posts right here. I think I have it linked underneath. But you can see this is the very beginning. It's like very basic patterns it's trying to find. Don't ask me right now about how they do this, just because we don't have enough time. But you can say like this is kind of like what the neural network is looking at, and this is kind of like what the image would turn into. And you can see like some of these patterns are here, they're varying patterns. And then as we get higher up into the convolution, more and more like sophisticated patterns are found. So you can see here, like, for example, different like spirals and stuff. So again, remember that basically that these filters are determined by the neural network adjusting basically those values you saw like over here. Essentially, it's just adjusting these values and what's optimal. And then when you take these parts, it's saying, all right, it's going to take this filter and say, apply it to the image, or like I should really say a portion of the image, and it's going to give a value. And it's hopefully going to maximize that value of saying, oh yeah, this pattern exists in this part. And essentially, hopefully the idea there at the very end is that it can say, okay, well, these patterns exist here. So this must be a dog, or this must be a cat, or this must be a person, or whatever it is that your image is doing. Okay. Yeah, Jessica.
Do we know what the original images were of?
Yeah, I believe so. The way you do this essentially is you feed it static, and you say, basically you just get static and say, all right, go ahead and find what maximizes this part. There's some ways you can do this. This is with visualizing. There's different ways you can do it. But this is essentially to visualize what the neural network is finding and what's optimizing for. And so that's what this, you can think of this more being like a blank sheet, in saying, apply your blank sheet to, like, apply your filter to this blank sheet, and these are the values that would come out from it. It's kind of like reversing backwards. So typically this is not actually like you wouldn't be able to like crack open the CNN and see these things in here. You kind of have to tease this out, which is why it's still a black box in a lot of ways. It's not something like It's just like there. It's like, oh, you have to tease this out, and this is where visualizing parts of CNN is going on. I just want to kind of.
Okay, so I just want to make sure I got what you just said. They fed this static, and this was the outcome?
I'm pretty sure. Let me see. It's from this direct blog from Karis, if I remember this right. And so I believe it's the same method that they use in the curriculum. This is why I'm going down links. Like it might take a little bit extra time.
I can look to it if it's like easier.
Yeah,
I can go check it out.
Yeah, if you want to check it out, that'd be good. Cool. Like I'll send in the chat right now. So there we go. Yeah, and you can kind of see a little bit of what's going on. It's essentially, it's not necessarily doing the convolution. It's kind of trying to work it backwards. Like you can see like this V process image and stuff like this here. So anyway, it's a cool thing to do. It also can help you with debugging what's going on with your convolution. All right. So I know I went a little bit over, not too bad. We did not get into NLP like I had hoped, unfortunately. But we will go, I guarantee we're going to go over it next time because I just want to make sure we spend that time. Quick thumbs up. Who's already at least touched the NLP section? I see some thumbs up. Cool. So just quickly, like, how are we feeling about NLP section? Like, pretty good? Yeah. Okay. Yeah, I think it's a pretty cool thing. We can, next time we'll try to maybe go through it really quickly about just like overall, like what's going on. And then the one part I did want to share with natural language processing, which I don't think that the curriculum goes through a lot, is embeddings in general, and like saying how are these built up and like what can you do with these embeddings. And it's really cool actually, what's going on. And I think I have a little, anyway, we'll talk about this in the future. But just to give you a little preview is one thing that we'll look at is something called TSNE, T-SNE. It's a really cool way to visualize embeddings and stuff like this. And so we'll actually go through a Kaggle notebook from, let's hear, yeah, this Kaggle notebook. We'll go through this next time and we'll kind of see a little bit like what this goes through. What's kind of cool is that it's not actually natural language processing by itself. They're actually using, in this notebook, the data scientist actually uses movie ratings, and basically based on movie ratings and who liked them and stuff like this, determining how they relate together. And it's a pretty cool set of notebooks. So we'll do that next time. And I think that's a good way to talk about NLP, embeddings, and say, well, what's embeddings? Can it be done more than just NLP? And it turns out there's a lot you can do. So that'll be next time. Okay.